This is section 9.9, part 2. All right, so we're working on geometric series representations of functions. And of course, there are only certain kinds of functions for which this will work. You have to be able to write it as a constant divided by 1 minus a function of x for this to work. And sometimes, as we saw in the last example we did, that may involve something like partial fractions as well. So it can become kind of complicated. All right, so let's find a power series representation for f of x equals ln of x, and the center is going to be at 1. Now, that is not writable directly as a over 1 minus r. So one of the things you're going to have to consider the possibility of is that is there a derivative or antiderivative of that function that is in that form? So I think you'll know that if 1 over x is considered, I'll call that g of x, that that is related to ln of x. So we're going to make that linkage between those two very clear in just a second. But let's just work with g of x equals 1 over x. To make that in a form that I would like, I'm going to need to have a 1 in there. So I'm going to add 0 to that in the form of, let me put this in a different color, 1 minus 1 plus x. Of course, that's looks different, but it's the same value as g of x. Let's see. Then I know with the center being 1, and that's, by the way, the reason I picked 1, not 2 minus 2 or 7 minus 7, but because I knew that I needed to have an x minus 1 in there. Okay, so that's negative 1 plus x plus 1. And you may be thinking, wait, what, did you put the right number with that? Well, actually, I think I did, because I need to multiply this by negative 1 over negative 1 for 2 reasons. That has to be a positive 1 in the denominator minus a function of x. So if I do that, oh wait, I think I'm wrong. Yeah, I'm wrong. Okay, let me back up. I just thought it through a little bit more carefully and decided I was not going to get the right answer. So let me restate that. Let's use the 1 here. Okay, let's use the 1 here plus x minus 1. And that gives us the x minus 1 we were hoping for. So the only problem now is that it has to be rewritten as a subtraction. So we do have the positive 1, and to rewrite addition as subtraction, it's going to be minus the opposite of x minus 1. And that's now in the form of a over 1 minus r, where a is positive 1 and r is the opposite of x minus 1. Okay, so that means that 1 over x is writable as a power series using the geometric form from n equals 0 to infinity of a, which is 1, times r, which is the opposite of x minus 1 to the nth. And of course 1 times anything is that thing. And negative 1 times x minus 1 inside of those parentheses means that we can distribute that power to each factor. So that's going to be negative 1 to the nth times x minus 1 to the nth. And it converges for values of x such that the absolute value of our r is less than 1. So the absolute value of negative 1 is 1 times the absolute value of x minus 1 will be less than 1. So that means that x minus 1 will be between negative 1 and positive 1. Then adding 1 everywhere to get x by itself means that our interval of convergence is 0 to 2. And again, we're not testing the endpoints because we treated this geometrically. Okay, so now we need to make the linkage to our function. We know our function is ln of x. We know that ln of x is the integral of 1 over x dx plus a constant of integration, which remember we like to put that in front. C plus, now the antiderivative of 1 over x, if 1 over x is the series we wrote up here, we're now going to take its antiderivative. So let's see, the antiderivative will be a series that starts at n equals something, I'll come back to that in a second, to infinity. And it'll be negative 1 to something. I'm going to call it n for right now. It might be n plus 1 or n minus 1 in a second. But the antiderivative of x minus 1 to the nth is x minus 1 raised to 1 greater power, so n plus 1, over that new exponent, that new power. And of course we already have the plus c. So let's write the first couple of terms of this up here. If n is 0, negative 1 to the 0 is 1, x minus 1 to the 0 is 1, so that'll be 1. Now put in 1, negative 1 to the first is negative 1, so that'll be minus, and x minus 1 to the first. Then the next one will be plus x minus 1, oops, wrote that wrong, try that again. That'll become x minus 1 squared, etc. Now, if we were to find the antiderivative of these things term by term, the antiderivative of that is x, or we could write x minus 1, right? Because the derivative of x minus 1 would be 1, minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus ... Kind of ran out of room over there. So down here we need to think about those antiderivatives being our answers. We want it to be x minus 1 minus x minus 1 over x minus 1 squared, excuse me, over 2 plus x minus 1 cubed over 3, etc. Oops, should be a minus. Dot, dot, dot. Okay, so what value of n would we need to start with to make all that happen? Well, if I'm putting n for n, the very first denominator is over an invisible 1. And so if n were 0 to start with, that would give me division by 1, and double check the numerator. That would be x minus 1 to the 0 plus 1, x minus 1 to the first. Okay, that looks good. Then we have to decide, is that power on negative 1 correct? If we start at 0, negative 1 to the 0 is positive 1. Our first term is positive. So I think it's all good in that form. And what we said was that if we have a series that we do the antiderivative of or the derivative of, it maintains the same radius of convergence. So it'll still be the same radius, which means it's the same interval, and we don't have to test the endpoints because, again, this is treated geometrically, so we don't have to worry about that, and it'll be the same interval of convergence as it was for g of x, which was 1 over x. Okay, so let's do one more example and see if we can draw this to a close. Okay, so f of x this time is inverse tangent of x centered at 0. Okay, so I'm trying to think of something related to inverse tangent of x that'll help me. And I recall that the derivative of inverse tangent of x is 1 over 1 plus x squared. And looky there, that is pretty easy to write in that form. Now, I'm going to show you a little trick here on this one to make it easier. Let's consider g of x to be 1 over 1 plus x. I think we did this one before. Pretty sure we did. Let me look through and make sure. It may have been in the last recording. It may have been in this one, but let me find it to be sure. Let's see, 1 over 1 plus x. Okay. We did 2 over x plus 1. And the only difference would be we wouldn't have that 2 in there. So if you just take that 2 out from an earlier problem, that will become sigma equals 0 to infinity of negative 1 to the nth. Remember, there's just no 2. That's the only difference. X to the nth. And its interval of convergence, well, r was x, so absolute value of x less than 1. So x is between negative 1 and 1. And that would be the interval of convergence for g of x. Okay, so just kind of keep that in mind. That's for g of x. Alrighty. So, well, convergence, let me just write that as an interval. Okay, now, instead of having to start from scratch, because we already knew what 1 over 1 plus x was equal to, we could substitute into that g of x with x squared, which is going to be 1 plus x squared in the denominator, which, as we saw earlier in one of those properties I mentioned, that's then substitutable into the formula we have. I'm going to take every x in this formula right above, and in its place put x squared. To the nth. And of course, a power and a power. Do a little simplification here. Negative 1 to the nth times x to the 2n. Powers on powers, you multiply. So, remember that's 1 over 1 plus x squared. That's what we just found. You circle that so that you are paying attention to where that is coming from. So, take the equation 1 over 1 plus x squared equal to our final answer for the series. And how will I take this to become inverse tangent of x? Well, what we're going to do is we're going to integrate both sides of this equation with respect to x. So that's going to be c plus sigma from n equals something, I don't know yet, I'll have to figure that out, of, oops, I forgot to put the n here, the power on n, and that'll be negative 1 to a power. I'll start with n and hope that works out, but then the antiderivative of a power of x is x to the power of x you have plus 1 divided by that new power, which is 2n plus 1. And let's see. Oh, and there's something I forgot to do in the last problem. I'll come back to it. We'll do both of them at the same time. What I'm thinking of in my head. Hope I don't forget. So let's see what we need to start with. So this series, if I put in 0, I'll get 1. If I put in 1, I'll get minus x squared. If I put in 2, I'll get positive x to the 4th, etc. And then integrating those terms, I would get the antiderivative of 1 is x. The antiderivative of x squared is 1/3 x cubed plus 1/5 x to the 4th, etc. And in order for that to be my correct answer, the first denominator for x over invisible 1 is 1. So if I let n equal 0, 2 times 0 plus 1 is 1. That's good. That would mean that the power on x is to the first, which is correct. And then if I put 0 in as the power of negative 1 to the 0 is positive 1. My first answer is positive. That's good to go. Okay. So now we have an answer for what, of course on the left side that's inverse, or arctangent, inverse tangent of x, or arctangent of x, is therefore equal to c plus the series represented by sigma going from 0 to infinity, negative 1 to the nth, x to the 2n plus 1 over 2n plus 1. Now, what I forgot to do earlier, and what I'm going to do first with this one, then I'll go back to the other one, is if there's any value of x in our interval of convergence, which since the interval of convergence for g was -1 to 1, and doing the antiderivative won't change that. So our interval of convergence is still -1 to 1. If there's a number in there for which we know a value of tangent inverse of x, then we can actually calculate what c will be for any known value. So what if I were to let x equal 0? That's certainly on the interval, right? It's between -1 and 1. So tangent inverse of 0 would be equal to c plus sigma from n equals 0 to infinity of -1 to the nth times 0 to the 2n plus 1 is 0. 0 divided by 2n plus 1 is 0. And so we know that the tangent inverse of 0 is 0. And the sum of a whole bunch of zeros is 0. And so c is equal to 0. So we know for sure now that tangent inverse of x is equal to 0 plus, so just whatever comes after plus, sigma from n equals, I was getting ahead of myself, from n equals 0 to infinity of -1 to the nth x to the 2n plus 1 over 2n plus 1. And again, just to clarify, the interval of convergence, when that's actually a series that converges to inverse tangent of x, is for any x between -1 and 1. That will work. Okay, what I forgot to do earlier was that same thing. We could solve for that c. So I want you to focus on this almost final answer. We need to pick some number on the interval. I'm going to change to different colors so you can see what's new. What if we were to let x equal 1? Do you know what the natural log of 1 is? Well, the natural log of 1 should be equal to c plus sigma n equals 0. Well, yeah, it is 0. We already figured that out. To infinity of -1 to the nth times, let's see, we're putting 1 in. 1 minus 1 is 0. 0 to the n plus 1 is 0. 0 divided by n plus 1 is 0. So again, we're going to get a whole bunch of zeros. On the left side, natural log of 1 is 0, is equal to c plus the sum of a whole bunch of zeros is 0, and so c is 0. So as it turns out, the natural logarithm of x is equal to 0 plus that series, so just the series, -1 to the nth times x minus 1 to the n plus 1 divided by n plus 1. And again, just for clarity, that works for the interval of convergence 0 to 2. Sorry I forgot to do that earlier, but I guess it's okay. We ended up doing both of them at the same time, which made it clearer what we were thinking about. All right, so that ends this lesson. I will see you in class.